time, but it's like parentheses x plus secant x to the fifth power minus 1. Then chain rule, right?
And then what do I do? I mean, there's no, that's it? There's not a power on the end?
Oh, yeah, it's all raised to something. Hold on.
Well, pick your favorite number.
5.
Right. Okay, we're going to take the first derivative of this thing.
Yeah.
So the 5 on the very outside is where we start. So we'll pull that way down in front, leave all of this alone, and raise it to the 4. And now we're inside. So I'll do my part. Derivative of x is 1. Now it's your turn.
Oh, sorry. I think this is where I got kind of confused. It's to the -3.
This is to the -3?
No, like the f of x is instead of 5, it's -3.
Okay. I can fix that, maybe.
So just a -5 is
I don't have an eraser. Not one in there either. Haha. Now we can continue. This is to the -3 out here?
yes.
Okay. Well, that brings the -3 down here. Then 1 power less makes us a -4. You good with that?
Yes.
Okay, now it was your turn. You're taking the derivative of the secant.
Which is secant of x. X times 1 times 5x.
And then we close it. That's it. Okay?
13.
So the important thing is, probably the one place where you could make a mistake is putting parentheses here, because this only goes with this last term.
Let me see. Yeah, because I tried to do that, and I'm pretty sure I got that because I remember having the -4 and the -3, and the other stuff is kind of like easy. So
Here's where you messed up then, because this is part I did. The derivative of x is 1.
yeah, I remember putting 1, 2, and then so that didn't work, and I didn't work, and then so I tried to move the whole thing, or I rewrote f of x as 1 over all of that, and then I tried the quotient rule, and that didn't work.
Huh, it should. You want to
So-
try entering it now?
It's closed.
Oh, I can open it. I have that power, only when I can see,
I might have missed like some parentheses or something.
perhaps. Let me open that old web workup. Huh, why is it not opening it? Just click on that then. This is assignment 6. Okay, now it's open. You said it was like problem 11. Nope, it's not problem 11. It is problem 13. X plus the secant of x fifth minus 1 all to the negative 4. Well, try it. Try entering that and see if it works.
Would I have to put the negative 4 in parentheses?
No? That's what's given us the solution, so it better work.
So for the 5x to the 4th,
Uh-huh.
I just put like.
You can just write 5x to the 4th. You don't need anything in between. It'll take it as multiplication.
See, yeah, because right here it says my, like, I guess my history of what I've typed before, and
Uh-huh.
I put the parentheses on the 5x plus 4. Isn't that what you said not to do? Look, that's what I typed in.
Yes.
I knocked over. So didn't you say not to do that?
Not to put the parentheses after
Yeah,
the
so
tangent.
that's what I thought. Wrong, I think.
Yes.
Yeah, so that's why I was wrong.
You gotta make sure the 5x to the 4th goes only with these two right in front, right here.
Nice.
Good. Anything else?
I couldn't find the second and third derivative. I got the first derivative right, but you want me to tell you f of x or the first?
Yeah, give me f of x.
F of x is equal to the square root of 4t squared plus 4.
Okay, so that's f of t then.
Yeah, right.
So maybe you started using x's when you were entering it in as your answer.
Mhm,
No?
mhm.
Okay, so this is 4t squared plus 4 all to the 1/2. Okay, and so your first derivative, go ahead and call it out to me.
4t parentheses 4t squared plus 4.
Okay,
Oh, in front of that is a 4t. Because you have to multiply.
because that's good. Let me do it all together. Let me not simplify it. Now there's an 8t and the derivative inside. Now that makes that a 4t in front. Did you then do the quotient rule or the product rule? Okay. All right, so let's do the product rule. T, we're putting an X there. Okay. So we got the first times the derivative of the second. Let's see, 1 power less gives me a -3/2 in here. Then the derivative inside gives me another 8t. That's the first times the derivative of the second. Plus the second times the derivative of the first, but the derivative of the first is just a 4. Maybe we should put some stuff together first. Let's put together all the stuff in the first batch. We'll put together the 4t, the -1/2, and the 8t. So this gives me a -2t times 8 is a -16t squared. Times 4t squared plus 4 to the -3/2 plus 4t squared plus 4 to the -1/2. That's the second derivative. And you said we need a third one? Yes. So we're sticking with the product rule.
So we would have to do two different products.
The second one's not a, that's just a constant, so you don't have to do the product rule here, but you will have to do the product rule there. So for the third derivative, we got the first times the derivative of the second, so here's the first, negative 16t squared. For the second one, we bring the negative 3/2 down. Take that to 1 power less. So I got a negative 5/2. And then the derivative inside gives me another 8t. Then we go the other way. The derivative of the first term there is a negative 32t times the second, 4t squared plus 4 to the 3/2. And now the other one, the 4 is a constant, so hang on to it. Bring the power down. The negative 1/2 hits the 4 and gives me a negative 2. Then let's raise that to 1 power less. Gives me another negative 3/2. And then the derivative inside gives me an 8t. So in here, I'm going to take the negative 16t squared times negative 3/2 to get a positive 2 into 16, 8, 8 times 3 is positive 24t squared times this 8t. So now it's going to be a t cubed, whatever 24 times 8 is. Positive 192 t cubed, 4t squared plus 4 to the negative 5/2. These last two terms are going to match each other, so we can combine them. I've got a negative 16t times that stuff to the negative 3/2, and a negative 32t times that stuff to the negative 3/2. So how about a negative 48t times that stuff to the negative 3/2? You can probably enter it like that.
Thank you. Wait, when did you get the
Let's see, this came from the second half of the product rule. The first half was copy this down, take the derivative of that. Then I copied that down and took the derivative here. And that gives me the negative 32t.
Find the derivative of negative 2e to the 2x to the
Right here. Okay. So the negative 2 is a constant. We can just copy it down. Then we use the derivative of the e to the u. The derivative of e to a power is itself times the derivative of the power. So I'm going to get the e to the 2x cubed here times the derivative of the power. And that's going to be 6x squared.
So you don't have to move like the down. It's just all like 2x.
Nope, you leave that alone, right? The derivative with respect to x of e to the u is itself times the derivative of power. So the power stays put. Okay? Got one? No, you don't? Anybody else?
Did you erase the third derivative?
It's up top. So here's the final answer right here. Says it's wrong. Good golly. T after 48.
Yeah.
Anybody else? You ready to move on to something new then? It's not new, it's just the chain rule, but it's a chain rule in another fashion. Up to this point, we've been taking derivatives of functions. And now we're going to take an equation where the x's and the y's are mixed up in an equation. And we're going to take the derivative of the equation using the knowledge that x is the independent variable and y is the dependent variable or the function of x. So in section 3.6, we're going to do something called implicit differentiation. Does anybody know the equation for the circle centered at the origin, say of radius 2?
X squared plus y squared is equal to 4.
There you go. That's a circle centered at the origin of radius equal to 2. But that's not a function. Remember, a function had to have the property that each x has only one y. So it's an equation as opposed to a function. I can write a function that gives me the top half of the circle, or a function that gives me the bottom half of the circle. The top half of this circle can be written as a function by solving this equation for y in terms of x. I would get y squared is 4 minus x squared, and then take the positive square root, and that's the equation of the top half of the circle. The bottom half of the circle, you can write the equation by taking the negative square root. Now, if I just do the top half, it is a function. And I can find the slope of the tangent line anywhere to that top half of the circle by taking the derivative of this. If I want to find the slope of the tangent line to a point that lies on the bottom half of the circle, I take the derivative of the one that gives me the bottom half. For instance, let's look at, let's just go up here and let's find the slope of the tangent line. That one's not working. At the point where x is equal to 1. Looks like it should be some sort of negative number. What's the matter here with all my greens? Let's go with red. So to find the slope of the tangent line, at the point on the top half of the circle, if x is 1, can anybody tell me what y is? When x is 1 on the top half of the circle, what's the y coordinate? How much? Square root of 3. Put a 1 right here, we get the square root of 3. So to find the slope of the tangent line at that point, we take the derivative of y is equal to the positive square root 1. I'll write it to the 1/2 power. And then we bring the power down, raise it to 1 power less, multiply by the derivative of what's inside. So we get 1/2, 4 minus x squared all to the negative 1/2. The derivative inside is a negative 2x. So if I write that with positive exponents, the 1/2 multiplies with the negative 2x and leaves me with that minus x. Then the 4 minus x squared goes on the bottom to the positive 1/2 power. And so when x is 1, I get the slope of the tangent line is -1 over 4 minus 1 is 3 to the 1/2. That'll be -1 over radical 3. And so if I wanted to find the slope at another point, I just use whichever one it describes, the top half of the circle or the bottom half of the circle. Implicit differentiation gives us an alternative to having to solve the equation for the dependent variable in terms of the independent variable. So here's another way we can do it. We can just ignore this step here, keep our equation, implicit differentiation is a technique that allows us to take the derivative in an equation as opposed to a function. All we have to do when we take the derivative of this equation is keep in mind that x is the independent variable and y is an implicit function of x. And y is some function of x. So that when you take the derivative of x, it's just the way you normally would. But when you take the derivative of y, you have to use the chain rule. The derivative of y is the derivative of the outside rule times the derivative of the inside rule. It's probably easier to show you than to write notation. Let's take our equation. And now we're going to take the derivative of both sides of the equation with respect to x. So I'm going to take the derivative here with respect to x. And then I'm going to take the derivative of the right-hand side with respect to x. So here we take the derivative of x squared, and all we get is what we think we would, 2x. But when we take the derivative of y squared, you have to treat this as a function squared. Bring the power down, raise the function to 1 power less, and then multiply by the derivative of what's inside. And it'll look like this. I bring the power down, raise that to 1 power less, times the derivative of what's inside. That's the chain rule part. Then across the equal sign, the derivative constant is still 0. Now we solve that equation for y prime. So I can subtract the 2x from both sides. Then divide by the stuff in front of the y prime. So we're going to divide both sides by 2y. And the 2's will cancel. We get that y prime is minus x over y. And then that still represents the slope of the tangent line. So if I want to find the slope of the tangent line at that point, I put 1 in for x, square root of 3 in for y, and we get the same thing. 1 over square root of 3 with the minus sign in front of it. So it gives us a way to take the derivative through an equation. Because there are going to be many times that we are not able to algebraically solve the equation for y in terms of x. So we wouldn't be able to do this part if we were forced to, we couldn't. But we could always take the derivative of terms in the equation. Just keep in mind that x is the independent variable. So the derivative of the x is done as normal. But y is a dependent variable. So you'll always tack on the y prime after you take the derivative of the outside rule. So let's do that. Let's go through some equations here. So find an expression for y prime in terms of x and y. So let's just take something like 5x cubed plus 4y to the 5th minus the sine of y is equal to, I don't know, 16. So you see the difference between an equation and a function? All my variables are mixed up with. It's not like a y is equal to. But you go through here and take the derivative of each term with respect to x. So over there, I wrote it in red. Here, I'll just say it. That's what we're going to do it. We're going to take the derivative of each term with respect to the variable x. So here I am taking the derivative of 5x cubed, and I'll get 15x squared. Now I got the plus sign, and I'm going to go and take the derivative of 4y to the 5th. But I keep in mind that y is a function of x. So we start by taking the derivative of the outside, bring the 5 down, raise the y to 1 power less. So 4 times 5 is 20. Y to the 4th, and then multiply by the derivative inside. Well, we don't know what that is representing, so we just use the notation y prime. Now we go over here to take the derivative of the sine of y. What do you think the derivative of the sine of y is going to be? Cosine of y times y prime. And I just took the derivative of the dependent variable. That's the chain rule. Then the derivative of 16 is going to be 0. Okay. Now we have to take this equation and solve it for y prime. So I'm going to keep the two terms that have the y prime on the left-hand side, and I'm going to subtract 15x squared to get it over there. Now there's a common factor of y prime. I'm going to pull that out. That's what my goal is, to solve for y prime. So if I pull it out of here, there's a 20y to the fourth left. And if I pull it out of here, I just have the minus cosine of y. And so my last step is just to divide by that stuff next to the y prime. So y prime is all by itself. And it's a negative 15 x squared divided by the 20y to the fourth minus the cosine of y. Okay. We start with an equation. We take the derivative of the terms within the equation. And then as you're doing that, you generate another equation that has three variables in it, x, y, and y prime. Then you solve that equation algebraically for y prime. All right, so I got some examples here. Okay. Find y prime, same thing. If this time the equation looks like 3x to the negative 2 plus the square root of y minus e to the y is equal to 1 over x. While I'm erasing, let me make sure that you guys can take the derivative of those four terms. We'll solve for y prime together. Let's just take the derivative here. So the first term is just a function of x, and its derivative is going to be negative 6x to the negative 3. This is the same as y to the 1/2. So its derivative will be 1/2 y to the negative 1/2. But now make a note that you just took the derivative of a y. What you get is the derivative of the e to the y. Times y prime. And then the derivative of 1 over x. 1 over x is the same as x to the negative 1. Okay, now let's keep these two terms here and add that one to the other side because it doesn't have a y prime on it. So I'm going to rewrite this with the y to the 1/2 on the bottom, which is a square root of y. So that's 1 over 2 square root of y times y prime minus e to the y times y prime. I'm going to write that as negative 1 over x squared. Now I'm adding that. And I'm going to write that as 6 over x cubed. Is that okay with everybody? You can leave the negative exponents. It just, to me, that's one of those little quirky things that I just don't like to do. We did that so that we have all of our terms with the y prime on the same side of equal sign. The next step is just to factor out the y prime. And when I pull that out, I get 1 over 2 squared of y minus e to the y as the other factor. So the last step is to divide by that stuff next to the y prime. Okay. Again, you start with an equation. You take the derivative of each term in the equation. Every time you take the derivative of something involving a y, you get the chain rule. Derivative of the outside rule times the y prime. Then you get the y prime terms together on the same side of the equal sign, back out the y prime, and everything else is just x's and y's. And it still has the same interpretation that this will give us the slope to the tangent line at any point. And all of our derivative rules still apply. We still have things like product rules, quotient rules, things like that. So my next example has x times the cosine of 4y minus y to the 5th is equal to 12 minus y. So what's different about this example? You've got to do the product rule right here. Okay, first times through the second plus the second times the derivative of the first. All right, so let's see if you're getting the hang of it. I'm gonna do the product rule first times the derivative of the second. So what you get is the derivative of the cosine of 4y. Times what? More 4y prime, right? Because the derivative of the 4y gives you a 4y prime. All right, that's half of the product rule. Now the other half, the derivative of that x is just 1, and then times the cosine of 4y. We took the derivative of an x, so we don't need y prime here. Okay, now we're taking the derivative of the y to the 5th. There's the minus sign. Bring the power down, raise it to 1 power less, multiply by y prime. On the right-hand side, the derivative of 12 is 0. What about the derivative back there with minus y? Minus y prime. Okay. Okay, so I have 3 terms that have a y prime on them. This one, and that one. So let's move this one over there. Take this one over here. Let's simplify this. Let's put the 4, the minus sign, and the x in the front. So minus 4x sine of 4y times y prime. Then we have minus 5y to the 4th times y prime. I'm going to move this one over here. So we're going to have a plus y prime. And then when I move that cosine over there, I get a minus cosine of 4y. You follow all that? Now I'm going to take the y prime out, put it way in the front. So in here I'll have a minus 4x sine of 4y. The middle term will be a minus 5y to the 4th. Now what do I have back here when I pull that y prime out? Just a 1, right? So plus 1. And then the last step is to divide by that ugly mess in the parentheses there. Minus cosine of 4y divided by all of that. Minus 4x sine of 4y minus 5y to the 4th plus 1. Question? Okay, so let's write the equation of the tangent line. Here's the curve x squared minus 4xy plus y cubed is equal to 6 at the point 5, 1. Given a point makes the algebra step a little bit easier. You can kind of skip all of this. And if you're given a point, you can go ahead and put it in right in the line where you first took the derivative. So that these are a bunch of numbers now. Now, one thing you need to be careful with is right here in the middle. Y. That's the product rule. So think of this as being the first term, and that one's the second. You might even want to take the sign with the 4x and make the whole minus 4x the first term. So start here, take the derivative of x squared, we'll just get 2x. And now here comes the product rule. So right in here, I'm going to take the minus sign with the 4. I'm going to do the first times the derivative of the second, plus the second times the derivative of the first. So the first is just minus 4x. And what's the derivative of the second term now? That's right. And then the second is y, and the derivative of the first would give me a minus 4.
I have a question.
Yes.
Why is it not 1?
Where? Here?
Why is the derivative of y not 1?
It's 1 times y prime. Right? You take its ordinary derivative, get the 1.
Oh, okay.
And then the chain rule part says multiply by the y prime. Okay, next we're here at the end to take the derivative of y cubed. Tell me what I'll get. Times y prime. And then across the equal sign, the derivative of 6 is 0. So at this step, instead of doing all that algebra, go ahead and plug the numbers in. X is 5 and Y is 1. And then we'll get Y prime after we do that. So X is 5, I get 2 times 5 plus a negative 4 times 5 times Y prime. Y itself is 1. So 1 times negative 4 plus 3 times 1 squared times Y prime is equal to 0. So let's see, this looks like 10 minus 20Y prime minus 4 plus 3Y prime is equal to 0. 10 minus 4 will give me 6. And then minus 20Y prime plus 3Y prime is a negative 17Y prime. We're solving for Y prime. I'll move that term to the other side and then divide by the 17. Well, it makes the algebra a little bit easier if you just push the numbers in there first. That's still interpreted as the slope of the tangent line. So the equation of the tangent line is y minus 1 is 6 over 17 times x minus 5. Y minus y1 is equal to m times x minus x. We all good? Let me see if you know what I'm asking for here. What am I asking for? The second derivative. See, everywhere I've written a y prime here, I could have chosen to use this notation here. They call that the Dirichlet notation. Dy over dx is the same as y prime. This is asking us to find the second derivative. So what we'll do first is exactly what we did here. We'll get y prime as a function of x and y. And then when you take the derivative of y prime, you'll get the y double prime. We got to hustle a little bit. We got about 2 minutes. That's 1 minute per derivative. So here we go. The first derivative is just 2x minus 8y cubed times y prime is equal to 0. So when we solve that for y prime, let me go ahead and move that one over so I can keep everything positive. Prime. And then divide by the 8y cubed. And if you want, you can go ahead and divide 2 into 8 and get 4. First derivative okay with everybody? Now for my second derivative, when I take the derivative of a y prime, I'll get y double prime. When I take the derivative over here, I'm going to use the quotient rule. So derivative of y prime is our y double prime. And then we're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So bottom is 4y cubed. The derivative of the top is just 1. So I'm now going to write it. Minus the top, times the derivative of the bottom. What's the derivative of the bottom?
12y squared times y prime.
Good. And then the bottom squared is 4y cubed all squared. But we want y double prime strictly in terms of x and y. So right here, I'm going to take this y prime out, and I'm going to put that in. So we have y double prime is 4y cubed. Let me write this as minus 12xy squared. Now I'm substituting out this y prime for that, x over 4y cubed. And then divide all this by 16y to the 6th. Okay? I won't simplify because we're out of time, but we don't even need to simplify. We're okay. All right, so you go one more step. Substitute out the y prime, so that everything over here is just x's and y's. You would simplify if you wanted a third derivative, right? Is that a good place to kick you out of here? There's so much more to this section. We're going to use implicit differentiation to develop formulas for the derivatives of our inverse trig functions. Then we're going to do something called logarithmic differentiation. It's an extended form of implicit differentiation that allows us to bring powers down. Okay, so we're about halfway through this section, and I put you a web work up just for your amusement and learning experience. Okay. Let me cut this off and I gotta run to my next class. How about y'all? You done for the day? I'm done. All right, let me shut this one down and go to my next room. Thank you, Riley.